good evening, everyone, again. Happy to have you here today. My name is Daniel Müller-Gritschnider from the Technical University of Munich in Germany. I'm one of the organizers of the German TinyML meetups. Today also Markus is here. He's also an organizer. And then we have two other people in our group, which is Carlos from Bosch and Alexis from Infineon. And we are, as part of the TinyML activities of the TinyML Foundation, we are organizing these meetups with different talks. So at the moment, of course, this is happening mainly online, but we, of course, also hoping that we can have some of these meetups sooner again, also in person. So just to give you a little bit of information how this would work today. Those who have been here before already know it, right? So we start usually off with a little bit of information about activities from the TinyML Foundation. Then we have the main part today, which of course will be the talk. And today we have a very interesting talk with the title TinyML FPGA Implementation for Condition Monitoring. And this will be given by two speakers, so Altaf Khan from Infxl and by Martin Kellermann from Microchip. And after the talk, of course, there is plenty of room for discussion. So really, please feel free then to also participate in a discussion. And then also what we usually try to do is when we finish off is that we kind of go more in a open discussion. So we invite everybody who is interested to stay in the call. And then we can just chat a little bit about TinyML topics or whatever you have in mind. Also feel free to bring up some topics you're interested in. And that usually also leads to some very nice discussions. Okay, great. So to get started, TinyML Foundation, that's basically a non-profit organization. And there are a lot of activities going on here. And the idea, of course, is to promote activities in the TinyML and, of course, also collaboration and networking. And of course, this is done also in a very professional way and, of course, also supported by sponsors. And here you can see kind of the list of current TinyML talk sponsors. So there are 3 strategic partners, which are ARM, Qualcomm, and Edge Impulse. And further partners are Deep Light, Maxim Integrated, Kitsu, Reality AI, and SynSense. And for example, if you would also be interested, if you come from a company interesting to support these efforts, then please get in touch with Olga, and you can see the contact information below. Then in this TinyML, next to these meetups, there are a lot of activities going on at the moment, exciting ones. So for example, there's one activity which is a vision challenge, where basically groups can submit solutions for a certain vision problem. And of course, that will be then, of course, in a competitive way. And if you're interested in this is also supported by Hexter.io. Feel free to get onto the website and look into the problem. And I think that's actually a nice activity kind of to get into the field. Now, then there is kind of a global summit. So this is kind of a global meeting where all the different activities come together. And this really grew a lot in the last years. So I think this year it were like 5,000 people. So I think it's almost exponential growth from the previous years. So you can see there's a lot of interest and activities going on in this TinyML field. And the nice thing about this is also there is a channel, there's a TinyML YouTube channel, and all the different talks you can find there. So if you're interested in this field, I really recommend you go to YouTube, you look into the TinyML channel. There's really lots of really interesting material there to be found from all the experts in this field. We will also have this year for the first time kind of joint European, maybe the Middle East Africa summit or forum, which will happen in June. And I think they says the deadline for abstracts was already May 1st, but I think it was even extended until the end of this week. So if you still want to kind of give a small talk there or present your results, feel free to go to the website And you just have to enter an abstract, and then you basically can see whether you get a slot there. Okay, and then a final announcement. So the next talk will be happening on May 25. This will be given by Kartik Thakore, and he will talk about building TinyML application using Rune. We have this very good looking speaker here first, which is Altaf Khan, who is the CEO from Infxl LLC. And he started his career already as accelerometer system engineer in the Silicon Valley, and is really an enthusiast about TinyML and bringing these deep neural networks onto really battery operated IoT endpoints. So we're really very happy to have him here. So I guess he's really one of the experts in this field, and very much looking forward to his talk. And I think today we will hear about an activity that was done jointly with Microchip, and also happy to have Martin here tonight, who is a marketing manager at Microchip, actually sitting here in Munich. It's very close to where also my university is. And before that, he has already an application engineer exciting, so he brings a lot of FPGA experience. And he will then also cover and tell us more about how they will bring the TinyML field onto the FPGA. So I'm very much looking forward to the talk. Thanks for both of you to taking the time and give this talk. And now I would hand over to Altaf, and looking really forward to your part of the talk.
Hello, thank you very much, Daniel. Very happy to be here talking to all these people in Munich. Today, our topic is TinyML, but the FPGA implementation of TinyML. And the use case that we are going to talk about has to do with condition monitoring. This talk, like Martin mentioned, has two parts. I'm going to do the first part, in which I'll talk about the data that we had and how did we train a very efficient and a very small deep network from it. And that deep network will be in the form of very simple C code. Then in the second part, Martin would explain how he used some FPGA tools to convert that into HDL. And he will also present results on the size, the speed, and also energy consumption. Before I start, I have a couple of questions. So please, if you could go to chat and give your answers to these questions. And we'll try to incorporate your answers in the remaining parts of our discussion. So the first one has to do with the FPGAs and machine learning inference. So what do you think is the main benefit of FPGAs as far as machine learning inference is concerned? So please enter your answer into the chat. I'll be very grateful. The second question has to do with the same thing, but in the context of IoT edge devices, that why should one use FPGAs to do machine learning inference for IoT edge devices? As you know, IoT edge devices, they are normally designed to be low power devices. So what's the main reason you want to use FPGAs in IoT edge devices for machine learning inference? And finally, when I talk to people, many times people who have not used FPGAs, they are hesitant to use them. So I want to know if you are one of them. And if you are, please tell us what is the main reason. So that during the talk, during the QA, we could try to fix that issue. So if you had to use FPGAs, why are you hesitant in using FPGAs for machine learning inference? So please enter the answers to these questions in the chat. I'll be most grateful. I'll give you a minute if you could just do that.
Right, should I forward them to you, or do you see the
No,
chat?
no. I can see that.
Okay, perfect.
So there are several. People are talking about security, for example. People like the reduced energy consumption aspect of FPGAs. And yeah, another one that I was expecting for the third one, that the tools are not easy to use. So we'll try to address that during our discussion. So let's move on. So let me tell you why I am interested in FPGAs as far as machine learning inference is concerned. The easiest reason is low latency. That is, FPGAs are inherently parallel. I mean, you can configure them as a parallel machine. So for neural networks, for example, you can configure an FPGA so that all the neurons in a single layer are computed simultaneously, not one by one, but concurrently, simultaneously. So that will give you very, very low latency. And Martin will show you some results on that. But the benefit that most people do not talk about is power consumption. In an FPGA, only those parts of the computation are implemented which are required for the computation. If you use a microprocessor has many parts. If your program is not using those parts, you still get some penalty as far as energy consumption is concerned. But in FPGA, you put exactly what you need. So therefore, energy consumption is optimized, minimized. And another benefit of FPGAs is that they're completely reprogrammable. That is, you deploy a deep net somewhere, and later on you want to change it, that's no issue. If you want to change the structure, if you change the parameters, no problem. You can do it as many times as you want. So this reconfigurability, so very high, very low latency hardware, which is very reconfigurable, which requires very low power to run. So that's why we are interested in FPGAs. So let's move on to today's use case. So Martin sent me a data set in which he wanted to infer the state of a fan based on some sensors on that fan. So the four states that he had defined for which he had collected data was the normal state, the low power state, the low voltage state, when the voltage that is being applied to the fan is reduced, and the stuck object state, and also the obstructed state. So obstructed and stuck object, they're similar, but different in terms of how much change is being made. And he wanted to infer these states based on outputs from these three sensors. A triaxial accelerometer, so this accelerometer has three outputs, a PWM and a tachometer. So based on these 5 values, he wanted to infer one of those 4 states of the fan. So if you look at the training data, he collected about 4 million data points. So what we did was we carved those 4 million data points into 3 subsets, one for testing, one for validation, and the largest one for training. And this is the end result of training. So after he sent me the data, this is what I sent him back. So as you can see, this is very simple C code. And this is the C code for a complete trained deep neural network. Only a few lines of code. And in those few lines, the dynamic lines, if you look at them, I've highlighted them. These are the 3 while loops and 1 if block. And if you look at those while loops, what is happening over there is just simple integer additions. And the if block is just a lookup table. If you dig down into this network, you will see there are 2 types of data over there. Some 16-bit integers, they are in ROM 16, and some 8-bit integers, which are in ROM 8. So no floating point, no 32-bit, no divisions, no multiplications. So this is a very simple deep network. And this is highly tuned in the sense that it's really optimized for FPGA implementation, because floating point operations, they take a lot of space. A multiplier, a floating point multiplier takes a lot of space. So we have gotten rid of both of those things. So all the data paths are either 8-bit or 16-bit. So a very small footprint for this FPGA. Another thing I want to point out is that this network, this train network that you see, if you do it for one project, it will look like this. If you do it for another project, the only thing that changes is the top part, that one line. That's the only project-dependent part of this code. So if you do a very nice implementation of this code in FPGA, then doing the next project is quite straightforward, because the only difference between the two networks will be that one vector that you see right at the top. Another thing I want to point out is the size. So this, we have this network, it has some accuracy, but what is the size of this network? So if you just look at the code is very small. If you compile this code for the deep net inference, on a Cortex M4, it takes only 110 bytes. So it's really tiny. But we also have this ROM16. So in this case, ROM16 has 1800 bytes. And there's another element called ROM8, that's 650 bytes. And RAM, we require 137 bytes. So that means we're talking about 3 kilobytes. So the total size of this network, everything included, if you want to run it on a microcontroller or a microprocessor, is about 3 kilobytes. So that's what I mean when I say TinyML. So in summary, this network it has simple data and simple operations. So that's what makes it so attractive for FPGA implementation. One of the requirements of this network is that the inputs have to be 8-bit inputs, and the outputs are also 8-bit outputs. So the input outputs of this network are all 8-bit. So real life data, the features of the problem, they are normally not 8-bit, so we somehow have to map them into these single bytes. So if you're using a conventional network, in a conventional network, many times the inputs are 32-bit floating point, and normally they are range limited between 0 and 1 or -1 and 1. As far as Infxl's network is concerned, the inputs have to be integers between -127 and 127. So how do you get to that? So what you do is you do your normal that you do with a conventional network. You do your normal pre-processing, and then just multiply by 127 and round it to the nearest integer. That's all that you need to do. Next, when we did the pre-processing, we calculated some parameters, pre-processing parameters in the form of offset and gain. And I named them offset and gain for a particular reason. And the reason is that, you don't have to do this pre-processing in the FPGA. You can do it elsewhere as well. Many times your data is coming from analog sensors and you have an A to D in between. So you can do this gain offset thing over there. Most of the A to Ds these days, they're programmable. You can program their gain, you can program their offset as well. So you can completely offload it from the network, and you can do it in the A to D. Or sometimes something else is happening. For example, these days, when you buy these accelerometers, many times they are 10-bit accelerometers. So the output is already digital. So 10 bits, if you have that, all that you need to do is ignore the 2 lowest bits, or in some cases, the 2 higher bits, and connect it directly to the inputs of the network. So in that case, really, you're not doing any practical pre-processing. So we take this pre-processed data and we split it in 2 files, one for features, the other one for labels. And we give it to our machine learning server, which trains many networks, and it uses TensorFlow for that and some proprietary algorithms. And then we do something interesting. Then we have what we call the model picker. The model picker will pick the best network, and you define the best network. The best network could be the most accurate one, or it could be the most accurate one which fits in, let's say, 4 kilobytes, or the most accurate one which has a running time of 1 microsecond, or the most accurate one, which consumes as at most 100 microwatts. So according to the project's needs, you can ask the model picker to give you the appropriate network. So what I'm trying to say is, in some cases, the most accurate network is not what you want. You have other restrictions, other constraints that you need to satisfy. And after that, the selected model goes to the model packager, which converts into that really nice C code that I showed you earlier. So now you have a very nice network in about a dozen lines of code, and it's in the form of very simple C. It will compile for every microcontroller, microprocessor that you can think of, or even DSPs. And of course, like Martin's going to show you, that you can convert that easily in a few minutes into an FPGA implementation as well. So one of the things I want to point out is that we have really simplified the structure of our network. So therefore, we are not able to process images or sound. So this is not a CNN implementation. This is not a convolution network. It is a straightforward, deep network. So the sort of data that we are interested in is coming out of accelerometers, pressure sensors, chemical sensors, taste sensors, flow sensors, electrical sensors. So we did the training, and these are the results. So results, I don't know, some would say they are pretty good, some may not agree with that, but the average accuracy, the average precision, the average recall, the average F1 score is about 96%, which seems quite reasonable. So now, before I finish, I want to make a couple of key observations. The first one is that what we have done over here is we have created the C code for FPGA implementation. And this C code is very ideally suited for FPGA implementation because of the lack of any 32-bit data, any floating point data, any multiplier, any divisor. So all we have is 8 or 16-bit data and 8 or 16-bit addition or subtraction. That's number one. That's why the size is very small. That's why the FPGA will be very efficient. The second thing, and I mentioned that earlier as well, that from project to project, the only thing that changes is that one line of code, that vector. So once you learn how to do it on a given project, doing the next project becomes quite straightforward. So somebody mentioned the FPGA tools, they're difficult to use. So, get one of these networks implemented. The next one will be quite straightforward. So with that, I conclude part one. So what I did was I took data and I converted that into C code, a deep network in the form of C code. Now, what Martin will do is he will take the C code and use some FPGA tools and convert that into HDL for FPGA implementation. I'm done.
Okay, Altaf, thank you very much for the nice first part. I think while we are switching slides, if there is some quick question now in between, we would be able to take it. And then I think, Martin, if you would like to start sharing your slides.
Sure. Let me do something here. I'm going to stop sharing now. Okay, I have stopped sharing.
Thank you.
Okay, so I think so far I see no. We could check now in the chat again. Okay, and there is coming one question, Altaf, and the question is from Iyub. He is asking, are you applying code optimizations?
Code, not really. See, what we do is we train our network. And when we train our network, all the optimizations are applied over there. So we don't simplify the network after it has been trained. We simplify it while it is being trained. If you use the standard approach, for example, ARM has that approach that you take a complex network and then you apply a set of steps to it to simplify it, like quantization, like getting rid of some neurons or some edges. We don't do that. We do everything during training. So our training has two objectives, not one. So the dual objective is, number one, minimize the error, and number two, minimize the complexity. So what we get at the end is that C code that you see.
Okay.
Now you can apply optimizations to that. For example, if you want to run that code on a microcontroller, which is a 32-bit microcontroller, you can use some tricks. For example, you could use some SIMD instructions. You can apply those sorts of optimization if you like.
Okay. Okay. I think he says thanks. So I think that you answered the question. And we have another question by Adam. Adam is asking, how would you compare this to a binary quantized network?
Okay, so this is not a binary network. It has a variable depth of weight. So not all weights have the same depth. The average depth is something like 1.05, but it has a variable depth. So we don't believe in applying the same quantization to every weight, or every weight for a neuron, or every weight in a layer. So we fine tune it for that particular weight. So I have no way of comparing the two. All I can say is that this network is as close to a universal approximator as you can get. And binary networks, they have similar properties as well.
Mm-hmm. Okay. We have one other question. Okay, there's a follow-up question. Maybe take this one first from Adam. So Adam is asking, is the pre-processing offset scale fixed, or is that found by the search?
Oh, we have to find it according to the data that we have. In fact, it's I just showed you the gain and the offset, but you also have to figure out what sort of pre-processing you want to apply. You can apply the standard one, or the robust one, or the min-max one. So it's a choice you make. So in this case, we looked at the medians and means. And in case when median and mean were very different, we applied the robust pre-processing. Otherwise, we applied the standard one. But again, that varies from problem to problem, feature to feature. But the end result is those two numbers. Doesn't matter what strategy you use, at the end, you get an offset and a gain.
Okay, then we have one more question by Suri. Suri is asking, I'm not sure if you can see that he's asking, C code is a C array like in TensorFlow. Is that?
No, this is simple C code. So if you have an 8051, it will work on it. If you have the simplest 8-bit processor, it will work on it. Any processor which runs plain C, it will work on it. It will work on every processor made by Intel and ARM or Apple or anybody that you can think of. It will work on every processor because it does not use any complex instructions. It's just addition, subtractions, while loop, and if. That's it, nothing else. And as you can see, these are the common denominators for all processors that you can think of. All DSPs as well. I'll include the DSPs in this range as well. And because we are using 8 and 16-bit, that's why the FPGA implementation is very compact as well, because, that's how FPGAs work. Okay,
so Suri, I hope this answered the question. We have another question in the chat from Vhtl. Is FFT done on the data before training? It's also pre-processing.
Okay, in this case, we did not do any FFT. This is not a time series problem. The prediction is based on the instantaneous values. But yeah, if FFT has to be done, it has to be done outside the deep network before the data gets to the deep network. And of course, that can be expensive.
Okay. So I hope this answered the question. Good. I think this, as far as I can see, were all the questions at this point. Then Altaf, thanks again for the discussion. And I think we can move on to the second part, and then we have also another chance to go into questions. So Martin, then please go ahead. The stage is yours.
Okay, thank you, Daniel. And thanks, Altaf, also for the explanation of before. So I also took the questions that came in. And one of the topics that I saw here, or a couple of topics, are low power, security, and on and off. And those are definitely topics that are important in FPGAs and where the Microchip FPGAs can also help you quite a lot. Before I go really into the depth of everything, I want to give you a bit of background on the Microchip FPGAs and what is special about them. So the FPGAs in themselves, they are more at the mid-class range. So going up to about 500,000 logic elements on the current PolarFire and the PolarFire SoC. And that's also what I'm using for this experiment and for the implementation of the DeepNet from Infxl. And there are also some families before that which are also available, the EQ2 SmartFusion 2, partially also with a processing system here on the SmartFusion 2 with an M3. But the current generation based on RISC-V, that's what I'm going to use today in our talk. So what's good on security? What's reliability? The special thing about the Microchip FPGAs is that they're based on flash technology or on Sonos technology, which is also a non-volatile process. And that means that you don't have to send in a bit stream every time that you power on the device. The configuration is stored inside of the FPGA directly on the floating gate of the flash cell, and they only need to be programmed once. That's typically in your factory, but you can also do that later on in the field if you need to do a field update. So that's also perfectly valid application. Also, thanks to that configuration inside of the FPGA, you don't have this long boot up time, this power on reset, the inrush current, but the devices are typically more or less instant on and then working on low power. Also, effects like the single event upsets, which are happening on SRAM-based FPGAs, cannot happen here based on the architecture and based on the technology. Maybe also a bit of background. So we are talking about machine learning in a really tiny net, but there are also bigger versions, a bigger brother of that. If you need to go for vision application, detection of objects, things like that, then definitely TinyML is not the way to go. But there are other parts. In our case, it's the vector blocks IP and the software development kit. And that then works on the usual suspects of Caffe, TensorFlow, and does the normal implementation and the normal conversion from a trained 32-bit floating point network into the trained network based on the 8-bit integers. And similar as on the TinyML from Infxl, it's also that we are working here on 8-bit data, as that is highly efficient to work on. Inside of the FPGA, you then have the FPGA, where the IP is stored, where it's implemented in the fabric using a normal design flow, and then the weights are stored in SPI flash or can be stored on DDR for interfacing, and then this IP does the detection of the incoming data and can report back on what has been detected or what has been recognized. But this is, compared to what we are talking today, this is way larger. It's still pretty efficient, but not as efficient and not as tiny as the TinyML. And this is what I was taking from Altaf. I was taking this application for condition monitoring. And I had several goals on that. So FPGA designs are typically out there. They have certain tasks to do, or also multiple tasks, industrial automation, control of a machine, and there is already something inside of the FPGA. Devices are typically not filled up to 100%, but there is some leftover space, which can be used for something else. And that's what we are using here. So kind of a side space, some leftover space, and add on the additional value, the additional functionality of a small neural network to detect the anomalies on the sensor data. So the sensor data here was, as a demo, just a fan that was running, and then we had different incidents, I will call them. So the abstracted was holding some paper in front of the fan. Then an object in the fan was taking a card and putting it in. So like you have it on a bicycle, you hear then this rotating noise. And that's something that I wanted to have detected just based on the data from the sensor. The sensor was connected via SPI, read out, and created some, in this case, 16-bit data, which wasn't really working directly with the Infxl net. So I got the data from Altaf on how to pre-process my data, so bring them down to the 8-bit integers. And with that, I could then feed my network and do the detection. That was then pretty simple to do. And the tools that I was using for that were not just Vhtl tools, because that's something that I can use. But if I have C code coming from somewhere, it's typically better to not try to manually convert that, but to use the appropriate tools. What I was using on the C code is the tool called LagUp This takes C code or C++ code and converts that into something synthesizable into HDL code. This HDL code can then be taken into a normal FPGA design and then be implemented just as a normal IP as you would get it from anywhere else. So what did I do inside of the FPGA? The diagram here shows this is the kind of fan that I was using. And then I was just sticking this fan here with to that fan, just with a bit of sticky tape, and then had the different situations that I wanted to detect. The sensor itself is connected to the larger system, to the FPGA or the SoC via an SPI interface, and read out from there. In here, on the RISC-V, which I have on the chip, I'm doing the pre-processing. And then as I was getting curious on the different results of the implementation, I was using two different implementations of Infxl's deep neural network, where I didn't really change anything here on the code. The code of the deep network is exactly what Altaf was sending me. And the only thing that I was changing was a bit of the surrounding. So the way the data is flowing into the recognition, and then also how it's recognized afterwards. In the C code that Altaf was showing, there's also a little test bench that is very simple and very easy to digest, but it needs to be changed a little bit to also be usable here on the FPGA. So what I wanted to have was not just a data pattern that is showing me which is the highest likelihood, but I wanted to have really 4 signals which were showing me this is the normal one, this is the abstracted, or whatever it is. And that's why I added a little bit of C code that was then doing a comparison on the data and then ending up into 4 bits for showing what is going on. The high-level synthesis tool, that's something that is available from our side. It's available on our website. So if you have a look for LagUp HLS, you can find the web page and then also get access to the tool. Inside of the device, you see here 2 slightly different implementations. Those are mainly on the interface that I'm using here on the FPGA on the SoC part. One is the Xc4 interface, and I'm putting in an Xc4 interconnect. And then here on the TinyML, I'm creating an Xc4 interface just by a couple of options that I'm setting in the tool, but I'm not really changing anything in the code itself. On the other side, I'm just taking a very simple Apb To Register interface where I'm putting the value for the deep neural network in and where I'm starting that core. And that's it. So really, in principle here, the same, but slightly different interfacing for just the sake to see how it affects the size of the overall design. This is here something that you will recognize. It's the very simple C code from Altaf. And then also here, the test bench. This is the test bench. Pretty simple. Originally, you just have a while loop. Something is copied somewhere. Then the inference is run. And afterwards, something is read back. Here, the DeepNet inference would be theoretically my top level, which I want to instantiate in the FPGA. However, as I don't want to interface with this here, with this array, I put something around it where I said, okay, I want to have for the register interface, I want to have a FIFO interface, which is just taking my 8-bit data. And then here are the batch output. Those are my 4-bit signals that I'm then actually looking at. And then here, the preparation of the data in the test bench. And out here, again, on the test bench, just reading from that FIFO interface and printing it on the screen for my test bench. Inside of the FPGA, where I'm taking this deep-net inference, the only reason I renamed it here was to have it separate from the original one so that I can see it. And then I have a load net, and then here the read operation vector from that RAM and compare value. Those are just my or my post-processing, so that I'm getting my 4-bit data. And this here is taking the data from a FIFO interface and preparing it for the deep net. No magic at all, really just pretty simple, straightforward C code, a couple of lines of code. And then, in principle, the same, but not here for a register interface, but an Xc4 interface. Again here, same structure. Also here, more or less the same structure on the test bench. The only difference is that I have now here just the FIFO interface visible on the top level of my FPGA design. And outside of that function, I have a pragma specified that the data going in there is going to be an Xc4 interface. But apart from that, everything, again, just preparing the pre-processing, taking the data from the Xc4 interface, running the deep net inference, and then reading out again from that net and bringing it to the 4-bit of data. Relatively simple, relatively straightforward, and probably maybe altogether 1 or 2 hours of work just for the typing and having things clean. Then bringing that into hardware, what did I use? The target for the hardware is the iCycle kit, which is a demo board from our side. This features the PolarFire SoC, which is the RISC-V processor-based FPGA. And then I have this sensor as an SPI, as a microbus socket connected up here on this socket. The board here itself, as you can imagine, is a little bit too large for directly putting it onto the fan. So I was just using that here as a demo vehicle so that we can see how things would be implemented. The FPGA design itself, also pretty straightforward and pretty simple. And that's again then going into the direction of the tools are complex. Not really. It's just kind of the initial step. Once you know a little bit where to go, it's pretty straightforward to put something in. What I have here is the MSS, so the microcontroller subsystem, and that has then several outputs. Here, the register interface, the conversion here from the MSS into the fabric, then the conversion, which is also just a bit of C code, a couple of lines of C code where I was taking the data from here, and then driving an 8-bit interface or a couple of 8-bit interfaces, and those are then going into the simple instantiation of the deep net. The other one is this Axie interconnect, which I can already give you as a teaser, which will be a little bit larger. And then here on the Axie interconnect, I'm feeding that into the deep net. And the output on both is just the theoretically 8 bits, as I was just putting in an int 8 as output. But of that, I only use the bottom 4 bits, and the others I omit in the implementation, then they will just be optimized out. Down here, that's a screenshot of the implementation. It's here showing the MSS, the processor part, and this here, the other area, that's the FPGA fabric that would be available on that chip. Those are the used instances for those 2 nets. Here, the slightly larger one is the connection with the Xc4 interconnect and the Infxl IP. And here, the slightly smaller one is the one where I'm just using the interface register and drive the net itself. The number themselves are, I would say, pretty impressive. So the Axie interconnect, that's just a normal IP, that's standard size. And then here, if I go for the TinyML configuration with an Xc4 interface, I'm using about 600 lookup tables and 900 flip-flops, plus then also one of the large SRAMs, which are block RAMs inside of the FPGA, which can hold up to 20 kilobits of data. The other one, which is really just slightly different configuration, slightly different pragmas, and a different interface. I have here, instead of the Xc4 interconnect, I have the Apb To Register Interface, and you already see a difference here. Just 5 lookup tables and 18 flip-flops, hardly anything. Then here, the register the TinyML with the register interface, and that here is about half the size of the Xc4 interface. Again, the Xc4, very nice to use, but a bit of complexity to handle and to be handled on the FPGA. So using that without the Xc4 interface already going by half. And again here, one of the LS RAMs to store the data that Altaf was mentioning for being really the one for this project. And looking just at the neural net itself, how large that is, 240 lookup tables, 340 flip-flops, and the 1 LS RAM. Really, really small. Pretty impressive for such a thing. Now, the other thing, small is good, but how much power does it take? And that was something where I was using the power analysis, the smart power, which is part of the Libero SoC software, and just open the design. And then I have the option to just go into the different parts of the design and see how much how much power is used. Here, LSRAM, 1.4 milliwatts for that application. And the logic, 1/4 milliwatt. This is the small one. And then here with the Xc interconnect, well, I would have nearly said doubled, but again, I'm talking here about, for the LSRAM, about 1.3 milliwatts, probably based here on the Vhtl analysis, but I would expect more or less similar number here. And the logic here, 1 milliwatt, because of the Xc4 interface. Hardly anything. If I now do the calculation on how much power actually is used and how long it takes, it's pretty impressive. The recognition cycle, that's something that I then did in a co-simulation using Mentor tools, the model sim simulator. It showed me that here at the 100 megahertz, where I can easily run this net, it took me about 350 clock cycles for one recognition, which equals 3.5 microseconds. And now, question is, how much power, how much energy do I need for one recognition? And that's done here, taking the 1.6 milliwatts from before, calculating it, multiplying it by the time, and I'm here at 6 nanojoule. Small number, great number, tiny number. But what does it mean? And 6 nanojoule is nothing that you could really imagine. So I was looking at where can you have a similar number. And the closest one that I was coming up with, the kinetic energy of a mosquito just flying around. And that has about 4 microjoule. So 3 orders of magnitude larger compared to one recognition alone. Imagine with one flying mosquito, you can run 1,000 recognitions of sensor data. And I would say that's not great, that is tiny. And going back also to the number of instances that I could theoretically have, going back here to this one here, if I would be filling up this device here, I could instantiate about 300 of those tiny machine learning networks. If I go for the smallest one that we have available here, I could be putting in about 30 of those. Pretty impressive number, I would say, on that. So all in all, really very simple to implement tools, pretty simple to use. LegUp HLS is pretty simple to use. And then the power consumption, not great, but really tiny. And then just as a summary, very simple to implement. Took me about an hour to get it, to understand it. Probably first quarter of an hour was really understanding what is this simple thing, where is the network, where do I have to look. But then once that was done, it was really just going very straight forward. The footprint at the power consumption, small, really small, tiny. And also my goal of having this as a side function in the FPGA, that was absolutely met. So from that perspective, really very nice, very cool, very tiny application. And with that, I'm at the end of my presentation and I'm open to questions.
We have one question already, which came in during the talk. So somebody asked, why not using SPI interface directly connected to the TinyML block? Power-wise, it might be more optimized since it is not using the MSS, the software part.
Yes, so that is definitely an option. The only reason why I did it the other way was personal laziness. I just wanted to do it that way, and it was pretty straightforward to hook it up. But yes, if you want to go for an optimized solution, then that is also an option. You would then instantiate just an SPI IP core or create it yourself, and interface to the outside, to the sensor, to the pre-processing, and bring the data into the TinyML. However, what I had as benefit on my side here for the MSS, the pre-processing, that was something that I could then just easily do on the MSS. The other thing is also the MSS in this case was mainly there because I was going for this board. But if I were to go for looking at something else, I don't need that. So I could just have a small FPGA, just a pure play FPGA without an SoC, and have TinyML implemented there and interface appropriately. So yes, there are different options.
Okay. I hope that this answered your question. Is there any more questions coming? Possibly, I would have a question regarding you said you could mount the FPGA. For example, if you will now take one of your very small FPGAs, you can mount it with the sensor basically on the fan. It would really become kind of a deeply embedded device.
Yes.
What would be then your power breakdown? Would you say that the major power is in any way in the sensor, and you would all the sensor processing will be a very tiny part? You showed a very small number. Or would you say kind of with a kind of device, there would also be some overheads just coming from the device, not directly from the TinyML part, and that would be comparable? Or how would it turn out, you think?
So I would typically not go for having just an FPGA for just this readout and for this TinyML. That's probably not the right application. If that would be something that might be something where you could go for a small 8-bit microcontroller from Microchip. But if you have something where the FPGA is already present, then adding the TinyML to that, that's the real beauty. And that's where it adds the value. There is the overhead, the static power consumption. There is also the other logic switching. There are the clock signals which are going on. That's something that also would add. But if you look at just what is required for that, that's where I'm coming with the 6 nanojoules. And really, it depends on where you are, but typically the use case would be add on for that for the existing design. But if you wanted to, probably you could also do it in just standalone if it pays off.
Okay, thanks. Okay, we have got already quite a few more questions in. There's another question. What would be the gain if you would convert to Vhtl without using the HLS tool?
So in principle, HLS does convert here to Verilog, and then I'm taking the Verilog and bring that into the GUI interface as an IP core. So LegUp HLS does exactly that one, and I didn't really want to create the network myself. I didn't want to try to hand optimize the C code into Vhtl, but I left it to the tools. And Infxl provides different ways how the C code is written, and those have also some implications in the tool. But in general, it doesn't really pay off to have manual work put in here. It's pretty good to work with the pragmas and rely on the network, on the tool to get a small network.
Okay, so I hope this answered the question. We have another question from Adam. He's asking, as these signals acceleration current are effectively time series, are you classifying over a window of measurements, or are you making a decision based on a single reading?
Let me answer that one. Yeah, we are just predicting based on instantaneous values. So the idea was that we'll try to see if we can do that. If that doesn't work, we're going to switch to time series prediction. But we didn't have to because, like I mentioned, we got 96% accuracy just by instantaneous values. So yeah, it's based on instantaneous values.
Okay. But your tool would support that also, right?
Well, pre-processing is not part of the tool. All the tool does is you give it data, it gives you a network. So the pre-processing is separate. And again, but doing that, taking the time series data and cutting windows out of it, that's a standard pre-processing technique. So it's not a big deal.
Okay. Let me quickly go and ask for the next. All right, so I think we had one more in the chat from Eyup. Should we expect some difficulties incorporating more complex neural network models on FPGA platforms, e.g. a simple feed-forward neural network versus a full CNN model?
The answer is probably not really. It depends on how you implement it. So here, TinyML is just the simple network. But if you want to go for something more complicated, it depends on how you do it. So you would probably then have your typical framework like TensorFlow or Caffe or whatever you would be using. And then you have the appropriate tool flow to implement something from there. And then it depends on how you do it. So the vector blocks IP that I was mentioning before, that's a coprocessor in principle. So a small processing IP that takes in principle a program to implement or to infer the network. But there are also other options out there to implement something out of those trained blobs into hardware. And then you would have the appropriate network built out of the individual network layers, and that would then be optimized towards the FPGA fabric.
Maybe I ask a follow-up question there. What about if you might have kind of, sometimes there are complex layers, right, in the networks, like a nonlinear, like say tangents, superbolicus function. Would you have to kind of come up with a hardware implementation for these ones, or is there any support, or would you move that maybe on back to the processor?
Okay, let me take a stab at that before Martin answers it. The network that I showed you, it is using a complex squashing function. In fact, it is tangent hyperbolic. So we implement in such a way that you don't see it because it's optimized for speed and size.
Okay, well, great.
Yeah. Martin, you want to answer the rest of it, that how do you do it in an FPGA?
So here, as Altaf said, it wasn't visible, but then if you would have layers which are not directly supported inside of that, that vector blocks IP, then you could hand it back to the processor and it would be handled there.
Okay, okay. Okay, I think we have one more question, which is, okay, this is more kind of, I think, a startup question. The question is, are there any inexpensive development kits to get started with TinyML on FPGAs? So like, how would you say you should get started? Maybe I guess this by way from student or so.
Okay, let me take a stab at that. So these are two separate processes that how do you then generate the C code? How do you generate the deep network? And then how do you implement on an FPGA? So if you have C code and if you want to implement an FPGA, there are kits available. I'm sure Martin can tell you more about it. So what you will do is first you will use Infxl service to convert the data into a deep network in the form of C code. And then you open up that Microchip kit and take it through the steps and have a FPGA realization.
Okay, I hope this answered the question.
Yeah, so maybe just adding to the second part. So once you have the C code, then the step forward would be going for LegUp HLS as a tool. You need to get that one. And then for the implementation, you can go for the free version of Libero, the Libero in the silver version. And then you have the choice of the different boards. There are boards around with the previous generation, so Smart Fusion 2. Those are, for example, from Trans Electronics, really pretty cheap ones, around about 30, 40, 50 euros. And there are some boards from our distribution partners like Arrow, EBV, Future. And there are also the boards that we have. So I was mentioning the iCycle kit. That's probably not directly towards students, as it has too many features which are also going into the price. But then there are kits like the Splash kit, or which are lower priced, or potentially also a version of the video kit. But those are more the high value kits. If you want to go for the more the student version, then it would probably be one of the kits from our distribution partners.
And as far as today's use case is concerned, this will work on the cheapest kit that Microchip sells. Whatever is the simplest possible kit, it will work on it because it's very simple. The size is very small.
Yep. And I didn't put it on there for or didn't directly compare it, but you can probably see this little kit here. This is the so-called SMF 2000, which is sold by Arrow and by Trans Electronic. This is my first interaction with the Smart Fusion 2. That's a really small board, has a relatively small device on it, and you can fit in that TinyML from Infxl.
How much does it cost, Martin?
35, 40, 50 euros. I don't know exactly. Round about that size. The implementation would look a little bit differently there. So you wouldn't see the block RAM, you would see more logic, as the device is slightly different. But again, that's the beauty of high-level synthesis. If you have something converted into the appropriate architecture, you don't have to worry about those details. The tool will take care of most of that.
Okay. And the LegUp is already like integrated into your dev flow. So you could, or is this something you have to get extra?
It's something that is extra. So we are currently in the early access phase with LegUp, but it's already on the web page, and people that are interested in have a chance of getting into the early access flow, and then later during this year, it will be open for public access.
Okay, great to hear. Okay, good. So I hope I did not overlook anyone, but I think we have went over all the questions. It works, right? So again, as I said, like these activities are done by TinyML, which is a foundation, which is non-profit, but of course, in order kind of to set it up professionally, there are a lot of sponsors who support it. You can see them here, and I quickly just go over them. So one of the executive sponsors is ARM. I guess this is known to everyone, and they are now also feeling they are the software and hardware foundation for TinyML. We have Qualcomm, which do advancing AI research to make efficient AI ubiquitous. We have DeepLight, and they use AI to make other AI faster, smaller, and more power efficient. We have Edge Impulse, which is saying you do TinyML for all developers. Maxim Integrated, which is enabling edge intelligence. And Kizo, which have their AutoML, which is an automated machine learning platform that builds TinyML solutions for the edge using sensor data. Reality AI, which is adding advanced sensing to your product with TinyML. And SynSense, which is working on real-time, always-on smart sensing. Okay, and as a reminder, then next week, or next week, actually, we have the next talk coming up from Kartik Thakore, and he will talk about building TinyML application using Rune. Okay, great. Then thank you very much again, Martin, Altaf, for the very nice presentations and the time you took to come here today. I think it was very interesting, very nice. And thank you also to everybody who tuned in today.